So, Professor Halpern, I would like to start this interview by asking you to introduce yourself, your career, and your interests.
My name is Nicole Halpern. I'm a theoretical physicist at NIST, the National Institute of Standards and Technology, and the University of Maryland. I work at the intersection of quantum information theory and quantum thermodynamics, and I apply the tools from this intersection to many different surrounding fields. I was an undergraduate at Dartmouth College. I earned my master's degree at the Perimeter Institute for Theoretical Physics and the Perimeter Scholars International Program. I was at Caltech for my PhD, where my supervisor was John Preskill. Then I was an ITAMP postdoctoral fellow at ITAMP, the Institute for Theoretical Atomic, Molecular, and Optical Physics at Harvard University and the Smithsonian Institution. After that, I moved to NIST to build my research group. We, as I mentioned, work at the intersection of quantum information theory and quantum thermodynamics. The basic idea of quantum thermodynamics is thermodynamics was developed during the 1800s, inspired by large classical systems such as steam engines. But thermodynamic concepts such as heat and work are very relevant to quantum systems. For instance, we need to cool quantum systems usually to very low temperatures in order for them to exhibit quantum mechanical behaviors, and cooling is a thermodynamic process. So in quantum thermodynamics, we extend the laws of thermodynamics to small and quantum systems. We identify how quantum phenomena such as entanglement can enhance thermodynamic tasks such as work extraction. And we identify thermodynamic phenomena that only quantum systems can exhibit so that we can use thermodynamics to understand better what the differences between the quantum world and the classical world.
This already anticipated the following question, and I would like essentially to ask you, since you touched apparently quite different fields, thermodynamics, quantum information, and you also wrote a book about quantum steampunk, the physics of yesterday, tomorrow, no? Which is a kind of a funny, so couple of words. Is there a common background on all these disciplines?
Yes, I see information theory and thermodynamics as having very similar flavors. Both of them are operational disciplines. So in each of them, we often think about an agent who has some resources and is trying to perform some task. We ask how efficiently the agent can perform that task. In thermodynamics, our agent might have access to a non-equilibrium system, like a gas that is compressed in a box, and we might ask how much work can the agent extract. In information theory, we might think about an agent who has a noisy communication channel, and we ask how well can the agent compress a message and send it across that channel. So in both cases, we are thinking operationally, and in both cases, entropy plays a very important role, or entropies. So entropies in thermodynamics tell us, and statistical mechanics tell us about how little we know the microstate of a system, given that we know macroscopic properties of the system. And in information theory, an entropy is similarly a measure of uncertainty about the outcome of a measurement of a quantum state or a random variable. The book Quantum Steampunk, which was written for the general public, but the general public does include scientists, has in its initial several chapters background information needed to approach quantum thermodynamics. So introductions to information theory, quantum physics, quantum information, and thermodynamics.
I think it is a quite interesting book. I haven't read for now. But another point is that you received the 2024 Herman Whale Prize for Young Scientists. What does it mean to you? Was it? I think it was quite important, receiving this prize.
I was very grateful to receive the prize, especially since I know a couple of people who had won the prize beforehand, and I very much look up to them. The Hermann Weyl Prize is a prize for studies of symmetry in physics, and I have spent a number of years thinking about non-abelian symmetries in thermodynamics. This research program was inspired by a very basic undergraduate statistical physics problem. Very often in statistical physics and throughout physics, we think about a small system interacting with a big environment. The two will exchange things such as energy and particles and maybe electric charge. And the small system, in many cases, will end up in a thermal state if the environment is in a thermal state at some temperature, and maybe chemical potential and so on. It turns out, well, for background, when we do quantum statistical mechanics, we represent the things that are exchanged by the system in the environment by Hermitian operators. For instance, the system of interest has a Hamiltonian and a particle number operator. The environment has a Hamiltonian and a particle number operator. There is a global Hamiltonian and global particle number operator. It turns out that in some important thermodynamic arguments, people for many, many decades had been assuming implicitly that these Hermitian operators that represent the things exchanged commute with each other. So the operators associated with the systems, energy and particle number and so on and so forth, commute with each other. And by the way, each of these quantities is conserved globally. And so we, in addition to thinking of these quantities as exchanged locally, we think of them as globally conserved quantities called charges, even if we're not referring to electric charge. So there's this implicit assumption of commutation of these conserved quantities in a number of thermodynamic arguments. But non-commutation is so important to very fundamental quantum physics, such as the uncertainty relation and measurement disturbance and quantum error correction. So some quantum thermodynamicists about a decade and a half ago started asking what happens to thermodynamic results if these charges don't commute with each other. Over the years, we found out that some key thermodynamic results change due to this non-commutation. And if a whole system, a system of interest, and environment composite has conserved quantities that don't commute with each other, these conserved quantities generate a non-abelian algebra associated with a non-abelian group. And so that's how this problem in quantum thermodynamics and statistical mechanics and many-body physics and information theory introduces an unusual type of symmetry into a field of physics.
Thanks. Oh, quite interesting, yes. So, speaking about statistical mechanics, this is a very difficult question. What do you think are, say, the future direction of this field of studies?
One of the directions that I'm most excited about is centered on this small growing subfield of non-abelian thermodynamics, or the thermodynamics of non-commuting charges. We still have a lot to do in this subfield. I think that we need to go around to every result in thermodynamics and chaos and ask, does anything change if we now assume that the dynamics conserve non-commuting charges? And if so, what changes? Can non-commuting charges or non-abelian symmetry, for instance, stave off thermalization to some extent? Additionally, and I think of thermodynamics and statistical mechanics as very much going hand in hand, so I sometimes refer to them almost synonymously, even though they're not exactly the same thing, of course. I think that now is a good time to look more closely for non-classical thermodynamic signatures. So we can sometimes identify some thermodynamic or statistical physics phenomenon that can be realized by a quantum system and not by any classical system. For instance, we can identify some thermodynamic signatures of contextuality. Contextuality is sometimes seen as resource that enables quantum computational speedup. It's kind of the power behind some forms of entanglement. And there are some thermodynamic phenomena that can signal contextuality, such as in some cases, certain values of thermodynamic entropy production. And that's something that my group has worked on. So I think that now is a good time to identify non-classical signatures within thermodynamics so we can better understand the quantum classical divide and maybe leverage these thermodynamic behaviors for quantum advantage.
Thank you. And so finally, what will your contribution to next StatPhys be about?
I'm very much looking forward to StatPhys, and perhaps predictably, my contribution will be in the subfield of non-abelian thermodynamics. The basic motivation is a common problem. Suppose that we have a metal wire that has a hot end and a cold end. Heat will move on average from the hot end to the cold end, and as energy moves, it generates entropy. So we can extend this example. Suppose that we have two different thermal systems. Suppose that they can interact so that they can exchange multiple quantities. For instance, energy, particles, or in the case of non-abelian thermodynamics, for example, the x, y, and z components of their spin. We can attribute a chemical potential to each of those conserved quantities associated with the first system, and we can attribute effective chemical potentials associated with those quantities to the second system. And if there is an imbalance of the chemical potentials, then quantities will tend to flow and produce entropy. My group recently found, in collaboration with Gabriel Londi, that this scenario is qualitatively different if the quantities that are moving back and forth are represented by operators that don't commute with each other. Conventionally, there are three equivalent formulae for stochastic entropy production. But if the quantities exchanged don't commute with each other, then these three formulae don't equal each other. There are three different now kind of flavors of stochastic entropy production. And each of those flavors of stochastic entropy production provides a different physical insight into how the non-commutation of conserved quantities can alter thermodynamics. One of those types of stochastic entropy production, if it assumes a value of a certain type in a certain set, can signal contextuality, the very quantum behavior that I mentioned earlier.
Okay, so I'm eager to hear your talk here in Florence next July. So see you there in summer, hoping not to that Florence will be not too hot. So bye bye.